Okay. So chapter 3 is on what's called naive set theory. And naive set theory is sort of the basic ideas of set theory um, that we all use in mathematics. Sort of formal set theory, um, that's a very complicated thing that almost nobody uses. Only people that actually study set theory for itself. And the problem is that naive set theory leads to paradoxes, various logical paradoxes. Um, so maybe we'll discuss that as we go on here. So we're just going to start with the definition. A set is a collection of just objects which are called the elements of that set. Okay, and elements of a set are presented in no particular order. There are sets that do have orders, but not all of them. It's not something common to all sets. So we write the following. X and then this epsilon A to mean element X is in set A. And we write the following to mean that it is not in set A. So we write X and then the slash through that element symbol to mean element X is not in set A. Okay? So for example, if I write something like this, okay, normally when a set is written, it is delimited by these braces, curly braces. And elements, if you're going to list them out, are separated by commas. So this is the set containing 5 elements. Elements. 4, 8, 7, 3, negative 2, in no particular order. Okay. I mean, when you present it like this, I mean, you wrote them in a certain order, but that order is not inherent to what the set actually is. So if I was to write this, 8, 4, negative 2, 7, 3, like that, this is the same set as the one we just presented, 4, 8, 7, 3, negative 2. okay, because there's no particular order to the elements of the set. This is the set containing 5 elements. Those 5 elements are 4, 8, 7, 3, and negative 2. All right, 4, 8, 7, 3, and negative 2. Also, elements can only be in a set one time. Every element is either in a set or not in a set. You can't say that it's in a set more than once. So if I was to write the following, 4, 4, 8, 4, 4, 7, 3, negative 2, negative 2, negative 2, is still the same set. Right? Elements are either in the set okay, they are never in a set multiple numbers of times. So, right, even though we listed 4 different times, it's still just in the set once. Now, it may seem kind of weird to say that, well, why would you describe the same element twice? And you'll see that, in fancier ways of describing sets, not in this way of describing them, just listing out the elements like that. In other fancier ways of describing sets, multiple descriptions of the same element can happen. So again, this is the set containing elements 4, 8, 7, 3, and negative 2. So it's just the same set as before. It's got 5 elements in it. Now, sets can contain anything as elements. Sets can contain anything as elements, including other sets. So, for example, here is a set containing the lowercase letter a, the number 3, a triangle, a hexagon, and this set here right, so this set has how many elements? 1, 2, 3, 4, 5. Has 5 elements. Okay, not 7 elements. One of the elements of this set is itself a set of 3 elements. Okay, however, it only counts as one element of the whole set. Right, so I've got this set. The first element is lowercase a. Second element is, not by first and second, meaning they're in order, just the way we see them here. This element is lowercase a. This element is the number 3. This element is an equilateral triangle. This element is an equilateral hexagon, and this element here is a set having 3 elements within it. But this thing here is only one set, this element here is one set, and that one set is an element of this whole set here. Okay, so sets can be elements of other sets. And that leads to the first paradox in naive set theory. So before we do that, so like here, therefore the following are true. Whoops. Can a set? Yeah, that's Russell's paradox. That's what leads to Russell's paradox. We'll cover that in just a moment. So the following are all true. So if I said 3 is an element of this set, it's true. Right? But if I said 5 is an element of this set, it's not true. This is false. 5 is not an element of this set. 5 is an element of this set. Right? 5 is an element of the set 2, 5, pi, but not this set, the outer set. Okay, 2, 5, pi, that set is an element of the big set here. Right, so, right, sets can be elements of other sets, but the elements of the set within the set are not elements of the bigger set. Right, so this example being the one here that I want to talk about. This set is an element of this. This set is an element of this set. Okay, the number 5 is an element of this set, but the number 5 is not an element of this set. Okay, so that should be clear enough. So now, like when you look at this, can a set be an element of itself? I mean, if you look at this picture here, is there any sort of thing like this going on? That's a picture of my screen showing a picture of my screen, showing a picture of my screen, so on and so forth. Is that sort of thing really possible? Or does that lead to some sort of paradox? Well, it does. Russell's paradox. So let A be equal to the set of all sets X, for which X is an element of X. The set X itself is an element of X. B is equal to the set of all sets X for which X is not an element of X. Now, what's problematic about this? What is problematic about this? One of the two is problematic. Which one is it?
A.
So A. So we ask, is A an element of A? Right? A and B are sets. A is the set of all sets, which are elements of themselves. B is the set of all sets that are not elements of themselves. So we ask, is A in A, or is A not in A? If A is in A, then A is an element of itself. So A should be in A. So that seems okay. It's B, actually, that's the problem. B is the set of all sets for which, sorry, is a set of all sets which are not elements of themselves. So if B is an element of itself, right, if B is an element of itself, it can't be, because by definition, B is the set of all sets that are not elements of themselves. Right? So B cannot be an element of itself. But if B is not an element of itself, then by definition, it belongs in B. It twists your mind a little bit, but you know. So if B is an element of B, then by definition, of B itself, B is not in B. Well, it can't both be true and not true. So if B, start with the other assumption, if B is not in B, then by the definition of B itself, B is an element of B. Huh, weird. So if you assume B is an element of itself, then by its own definition, it's not an element of itself. If you assume B is not an element of itself, by the definition of B, B must be an element of itself. So that's the paradox, right? These, like neither statement gives a consistent neither statement yields a consistent. Neither statement is consistent. Consistent means there's no contradiction. A contradiction is when you say, the proposition A is true and proposition A is false. Proposition A is both true and false. Well, it can't be. A proposition is either true or it's false, not both. Okay, but here we have this proposition is true leads to that proposition being false. This proposition being false leads to this proposition being true. Okay, neither one works. Neither statement is consistent. So this is the paradox, Russell's paradox. Has anyone taken any philosophy classes? Philosophy classes on logic? So this is often presented in philosophical circles in a traditional sort of way. In another sort of way. Has anyone heard it? Right. So in this town, so in philosophy classes, it's often presented in this fashion. So in this town, there's a barber, and this barber, he shaves every man. It's a male barber. This male barber, he shaves every man who does not shave himself in town. He shaves every man that does not shave himself. So who shaves the barber? Right? Who shaves the barber? If he shaves himself, right, then he can't shave himself because by definition, he only shaves people who don't shave themselves. So if he doesn't shave himself, then by definition he has to shave himself. Right? So it's similar to Russell's paradox. So axiomatic set theory or formal set theory is designed to get around this kind of stuff. But it's uber complicated, and there's really no need for it because most of the time we're not dealing with things that lead to these sorts of paradoxes and inconsistencies. Okay, so with that out of the way, I think I found I thought of another mathematical gold nugget that we should do related to this stuff. Does anybody know this brain teaser about the two brothers? One always tells the truth and one always lies. Has anyone heard that one before?
Yes.
Yeah. So you're walking down the road and you come to the fork in the road. One fork, goes to your destination. The other fork goes to certain doom. Standing at the fork of the road are two identical twin brothers, and one always lies, one always tells the truth. You have one question to ask them. What question should you ask to know which way to go? Um, so, um, we should go over that. And then I've got one that's even a little, well, it's a lot more difficult than that one. We'll go over that. That's an interesting one, dealing with negations and such, definitions and negations. All right, so but think about this one in the barber. Think about this in the barber. Try to really understand why we've got a paradox here. You got to say it to yourself a few times before it really sinks in. Okay, the set builder notation. So when we write the following, this is what it means. So this means, and these symbols are read in the following order, the set of all elements X such that P of X is true. So you read it in that order. The set of all, that's this symbol. Elements X, that's this symbol. Such that P of X is true. And sometimes it's written like this. Instead of a straight line, they use a colon. Set of all elements X such that P of X is true. Usually in typeset notation, you'll see it like this, and in handwritten notation, you'll see it like this. Not that that's always the case. I mean, either one is used. So the set of all elements X such that P of X is true. Once in a while, you'll also see this. Given a known set A, you will see the following. Well, let me copy that whole thing, actually. Given a known set A, sometimes you'll see this. Elements X in set A. So you've got this known set, and you're creating a subset of that known set. And so they'll write X in A. All right, so for example, so here are some known sets. That we can work with to do set builder notation. The set of natural numbers. And, you know, depending on who you ask, it either has the 0 in it or doesn't have the 0 in it. The distinction is not important. The set of integers, so this is the natural numbers. And I'll tell you why the distinction isn't important, but why I use this one. There's this one, this z, and that's the set of integers that is all whole numbers, including the negative ones. Oops, -1, 0, 1, 2, 3, ... The integers, the z comes from the German word Zahlen. And then using, oh, and so there's also z plus. So I use n to have the 0 because z plus would be the positive integers.
By the way, it's pronounced silent.
Oh, okay. Thank you. I had to. So in high school, I studied Spanish, and I speak. Aside from that, I speak Arabic fluently. But when I was in graduate school, it used to be when you wanted to get a PhD in math, you had to learn how to read math papers in 2 or 3 languages aside from English. I don't know if they still do this nowadays, but it was German, French, and Russian. So the French, I was okay with that because, you know, knowing the Spanish, learning how to you're not learning how to talk, you're not learning how to write, you're just learning how to read, how to decipher a paper, a mathematical paper in that language. So the French wasn't too hard, and you know I managed that one. But then they I wasn't going to do Russian because I didn't want to learn a new alphabet. So I started in on the doing the German, and I just had a really really hard time with it because I never encountered anything like it, and I wasn't to start learning a whole language from scratch is not that simple. So.
It's actually a really logical language, German.
I know. I mean, of course it is. I mean, there's millions of people who speak it. So, I mean, of course it's it's definitely well formed and makes a lot of sense. Just I was so unfamiliar with it. I had a really hard time with it. Anyway, so that I mispronounced it is not surprising. Okay, so now that we have these known sets, consider the following. The set of rational numbers is as follows. So it's this Q with this neat little sort of boldface notation. It's the set of all A over B such that A is an integer, B is an integer, and B is not 0, of course. Right? So the set of all elements A over B such that A is an integer, B is an integer, and B is not 0. So here the predicate actually has 2 entries in it, but that's fine. You could have as many entries as you need. So here we also have multiple descriptions of the same element. Right? So some elements of Q are, well, 5 is in Q because it's 5 over 1, right? 2/3 is in Q, but 2/3 is also equal to 4/9. Is also equal to -4 over -9. Right? So you have multiple descriptions of the same number within the rationals, right? Multiple description, infinitely many descriptions of the same element within the rational numbers. Also, 0 is in Q, because 0 is just 0 over 3, or whatever you want to put on the bottom. Anybody know some numbers that are not in Q?
Pi and E.
Mm-hmm. Well, pi, yeah. E, Euler's constant E, the one from calculus. Square root of 2. It's not in there. That proving that pi and E are not rational is takes a little bit of doing. It's not so simple. Showing that the square root of 2 is not rational is definitely doable. And we'll do that at some point. That'll be one of the nuggets that we present at some point throughout the semester. The golden ratio, that number that we were talking about last time, it's not in there. Any square root that's not a perfect square, any integer that's not a perfect square, when you take the square root, it's not in Q. Square root of 2 being the simplest one to analyze.
Wait, did you say 2 over 3 equals 4 over 9?
It doesn't, does it? It's 4 over 6. There you go. Sorry. So on and so forth. Okay, so that's the first example of set builder notation. Here's a few more. So let's do the set of all x such that x is an integer and -3 is less than or equal to x is less than 4. What is this set? So that's the set builder notation, but what is that set actually? Just listing out the elements explicitly.
Just integers from -3 to 3.
Yeah, integers from -3 to 3. So it's -3, -2, -1, 0, 1, 2, 3. Not including 4, right? Because it's strictly less than 4. How about this? The set of all x such that x is an integer and there exists y such that y is an element of the set 1, 2, and x equals 2y. X, the set of all x, such that x is an integer, and there exists a y in the set 1, 2, and x is equal to 2y. It's a very simple set, but I've just kind of made it more sort of obscure by using the set builder notation. The set of all x, such.
Wouldn't it be 4 and 2?
Just 2 and 4, yeah, that's it. Right? The set of all integers, x, right, such that, the set of all x, such that x is an integer, and there is a y in 1 and 2. Well, there's only two things there to choose from, y equal to 1 and y equal to 2. And, well, what's x? Well, in relation to y, it's completely determined. It's just equal to 2y. So we just have either y is 1 or y is 2, and x is 2 or x is 4. 2 times 1 or 2 times 2. Okay? So that's set builder notation. Now, by the way, you could also write these as follows. So you could also write the set of all x in Z. So this is actually a little more compact. The set of all x within the integers such that minus 3 is less than or equal to x is less than 4. Similarly, for this one, you could also write the set of all x in Z such that there exists y with y in the set 1, 2, and x equals 2y. All right, so because we're using that known set to define these sets that we're talking about, the set of all x such that x is in Z. Okay, so we're automatically defining a subset of Z, subset of the integers. So in which case, instead, you could write the set of all x in Z satisfying something. The set of all x in Z satisfying something. So these signify that the sets we're defining are subsets of Z. So you could write them this way, or you could write them this way. Okay. Subsets. So might as well talk about subsets. So we say that A is a subset of B. So this is read as A is a subset of B. When the following predicate statement What's the predicate statement? You remember how I was saying implication is really a containment relationship? Here it is. So it's more properly said in predicate logic, although you can think of it in propositional logic as well. So what is this predicate logic statement we're getting at for subset? For all x, what? If you want to say A is contained in B, or A is a subset of B.
X is an element in A implies X is an element in B.
Precisely. So when the following predicate logic statement is true, so the diagram to look at here is set B, here is set A, and then any element X that you choose that's contained in A has to also be contained in B. If X is an element of A, then X is an element of B. Yeah? If X is an element of A, then X is an element of B. So this means this picture depicts A as a subset of B. If you had something like this, so like this is set A and that's set B, and I got some element X right here. So in this picture, X is an element of A and X is not an element of B. Right? When is an implication false? When is an implication false?
When the hypothesis is true, but the conclusion is false.
When the hypothesis is true and the conclusion is false. That's exactly what I'm depicting here. In this picture, let's make it predicate logic. There exists X such that X is an element of A and, I'll use the X is not an element of B, which is the negation of this. I need to do this a little better. Actually, let's do the following. Let's do it all on another page. So here A is not a subset of B. So we talked about the negation is, right, the negation of a universally quantified statement. The negation of a universally quantified statement is an existentially quantified statement, right? For all X, P of X, negated is there exists X, P not X. So you take the quantifier, you flip it, and then you negate the predicate logic statement. It's not just a predicate by itself, it's a whole predicate logic statement, right? So for all X, A implies B. The negation is there exists X, not A implies B. But not A implies B is A and not B. Right? That's De Morgan's law. So if X is an element of A, then X is an element of B. As opposed to the negation, there exists X such that X is in A and X is not in B. So this means A is a subset of B. This means A is not a subset of B. All right, so implication, properly describes this containment relationship. And a containment relationship, subset relationship, properly describes the implication connector. So it's all very, very. So that's another reason why, when the hypothesis is false, you consider the implication to be true. I mean, if you're looking at an element out here, right, it's neither in A nor in B. It should have no bearing upon whether it should do nothing to determine if A is a subset of B or not. So this shouldn't be true, right, and this should be false. So that's another reason.
I have a question.
Yeah.
So, this might just be a notational difference too, but for the symbol that represents a subset,
Mm-hmm.
I've seen some people write it without the little line under it.
That means proper subset.
Okay, so there is a distinction between writing it without the line and writing it with.
Yeah, right. So, well, let's put that out there. When we write A like this, proper subset of B, we mean A is a proper subset of B, all right, which means A is a subset of B and A is not equal to B, right? Because, for any set A, A is a subset of itself. It's just not a proper subset, right? When two sets are equal, right? This is a true statement. If X is an element of A, then X is an element of A. That's true. It's true over any domain, right? Because true implies true is true, and false implies false is also true. Right? Any set is a subset of itself, but oftentimes we want to sort of disregard. We want to disregard the the case that A may be a subset, or sorry, we may want to exclude among all subsets of A. You might want to exclude the trivial one because A is a subset of itself. So when we write this, we mean A is a proper subset of B without the line. So it's kind of like less than or equal to, and strictly less than. Okay. Sometimes people write A, B to mean A is a proper subset of B. Although this notation is overkill, I think. So is subset but not equal to. Subset and not equal to, or something like that. That's kind of overkill. There's no need for that. All right. So what to say? Definition. When we write this thing, okay, it's a circle with a line through it. This denotes the empty set. It is a set with no elements at all. Sometimes, albeit rarely, the empty set is denoted by sometimes people like that. In computer science type in computer science type situations, people might write something like this to mean the empty set. Okay, but this is like really traditional. Everybody uses this. So how about this? Right? So this statement is what?
True.
True over any domain. Oops. Because because this is always false. Right? The hypothesis is always false, so the implication is always true. Right? So the empty set is always a subset for any set A. And A is always a subset of itself. So those are two sort of, trivial or cheesy examples of subsets. So there's a nice concept to get into next, but before we do that, we need the following. The order or cardinality of a set A is denoted by, and it equals the number of elements in A. So, for example, what's the cardinality of this set? Or the order? How many elements do we have in here? Remember, an element can be in a set just once. 4?
Yeah.
3, right? 1, 3, and 5.
Oh yeah, 3.
Well, actually, maybe I shouldn't use it 3. 1, 2, and 5. But is 3. The cardinality of the empty set is how many elements in the empty set? It has no elements in it. The cardinality is come on, guys. It's not
0.
0, of course. All right, it's only set order 0. All right, so the empty set has order 0. All right, and if A has order 0, then A must be equal to the empty set. Right? These other sets, right, Q, these other sets are infinite. Now there's different grades of infinite sets. Not all infinite sets are made alike. There's a smallest size of infinity, and then there are larger sizes of infinity. And if that sounds a little bit weird, well, yeah, it is. It's very weird. And I will, introduce you to that later, although it's not going to be something that you're going to be held responsible for in the course. It's definitely something you want to see because it's pretty cool. Like Z is the integers, that's the smallest, or the natural numbers. That's the smallest infinity. It's called countably infinite. Countable because you can count them. Not count them, you can enumerate them. There's a first element, second element, third element, fourth element, fifth element, 100th element, millionth element, 10 gazillionth element, so on and so forth. You can assign a natural number to each element. You can do the same thing with the integers. Right? You can assign a number to each element. So 1, first element is 1, second element is -1, third element is 2, fourth element is -2, and fifth element is 3, sixth element is -3. So basically, the integer x is element 2x minus 1, and -x is 2x is just 2x. And 0 will be the 0th element or something like that. So you can enumerate the integers, you just got to hip hop back and forth between positive, negative. Believe it or not, you can actually enumerate Q as well. So Q is no bigger than N because there's a 1-to-1 correspondence between the natural numbers and Q. It may seem unbelievable, but I'll show you how that goes later. You don't start getting larger infinities till you look at the real numbers. And we'll do that later. Okay, so we've got order or card. Oh, it's 117. So that's all for the lecture for today. Next time we'll take up more of this, or maybe I'll post it on YouTube. I will email you and let you know.